Immunology Insights, Basics and Beyond, Chapter 54, Mechanisms of Allergic Reactions. Marcello here. Welcome back to Immunology Insights, Basics and Beyond. In our previous chapters, we explored how infections from HIV and tuberculosis to influenza and emerging viruses challenge and sometimes evade the immune system. But if infection shows what happens when the immunity is too weak or misdirected, today's topic shows the opposite. What happens when the immune system goes too far? We first met allergic reactions briefly when we discussed hypersensitivity, but now it's time to look deeper at the molecular mechanisms that turn harmless antigens into triggers of inflammation. This section follows our exploration of infectious diseases to illustrate how an otherwise protective immune system can also overreact to benign antigens, linking defense mechanisms with dysregulation. So let's talk science. What is actually an allergic reaction? Allergies are hypersensitivity reactions caused by an exaggerated immune response to otherwise harmless antigens such as pollen, dust mites, or foods. At the core of this reaction lies, as discussed before, type 1 hypersensitivity, an IgE-mediated immune response orchestrated by Th2 cells, mast cells, and eosinophils. As step 1, we have the sensitization. When first exposed to an allergen, antigen-presenting cells such as dendritic cells present the antigen to naive T cells, steering them to become Th2 cells. These Th2 cells secrete cytokines like IL-4 and IL-13, which signal B cells to class switch and produce allergen-specific IgE antibodies. These IgE molecules bind to Fc epsilon receptors on mast cells and basophils, arming them for future encounters. As second step, we have the re-exposure. Upon re-exposure, the allergen cross-links these bound IgE antibodies, triggering mast cell degranulation and the release of mediators such as histamine, prostaglandins, and leukotrienes. This causes vasodilatation, tissue swelling, mucosecretion, and smooth muscle contraction, producing the familiar symptoms of allergy, itching, sneezing, or even bronchoconstriction. What are the players behind these reactions? First, we have the mast cells. They are the central effector cells releasing histamine and inflammatory mediators. Second, we have the eosinophils. They are recruited by IL-5 and release cytotoxic granules that can damage tissues. Third, we have the basophils. They are the circulating counterparts to mast cells that amplify Th2 responses. Fourth, we have the Th2 cells. They are the conductors of the allergic orchestra, producing IL-4, IL-5, and IL-13. And on the fifth spot, we have the regulatory T cells or Tregs. They normally keep inflammation in check, but often function suboptimally in allergic individuals. There are of course local and systemic effects. Depending on where the mast cell's activation occurs, allergic responses can vary dramatically. In the skin, we have urticaria or atopic dermatitis. In the airwaves, we have allergic rhinitis or asthma. In the gastrointestinal tract, we have food allergy. And systemic, we have anaphylaxis, a life-threatening reaction marked by vascular leakage, hypotension, and airway obstruction. With all that fuss, why do allergies exist? From an evolutionary perspective, IgE-based immunity likely evolved to combat parasites, especially helminths. Mast cells and eosinophils are highly effective at expelling large parasites but can cause collateral damage when misdirected against innocuous antigens. In an industrialized society with fewer parasitic infections, this system may have become miscalibrated, leading to a rise in allergies, a concept known as the hygiene hypothesis. The hygiene hypothesis proposes that reduced exposure to microbes, parasite and early life infections in cleaner, industrialized environments leads to an undertrained immune system. Without these early microbial lessons, the immune balance skews towards allergy-prone Th2 responses, making harmless antigens more likely to trigger inflammation. An interesting but also worrying fact is the transition from acute reaction to chronic disease. Repeated allergen exposure drives chronic inflammation, tissue remodeling, and recruitment of additional immune cells. This transition from acute allergy to persistent inflammation sets the stage for asthma, which we will explore in detail in the next chapter. Allergies, of course, have clinical and global relevance. They affect more than one-third of the global population, with prevalence continuing to rise. While most allergic reactions are mild, severe cases, particularly anaphylaxis and allergic asthma, remain major causes of emergency visits and deaths worldwide. Understanding these mechanisms is not merely academic, it's the foundation for targeted treatments that can restore immune balance. Topics that we'll tackle soon. Let me give you some examples of allergies. While most allergic reactions are mild, some can be dramatic and life-threatening. Some are severe, some are unusual. Peanut allergy, for example, is among the most severe. Trace exposures can trigger rapid onset anaphylaxis with airway swelling and circulatory collapse. Insect venom allergies, especially to bees or wasps, are another major cause of fatal anaphylaxis, where massive mast cell degranulation causes profound hypotension within minutes. Drug allergies, such as those to penicillin, can provoke widespread hives, angioedema, and even multi-organ failure. Food allergies beyond peanuts, like shellfish, tree nuts, or sesame, are increasingly common, particularly in Western countries. Less frequent but fascinating examples include exercise-induced anaphylaxis, where physical activity after eating a trigger food provokes collapse, and cold or sunlight-induced urticaria, where environmental stimuli activate mast cells directly. These cases remind us how diverse and unpredictable allergic disease can be, ranging from nuisance reactions to sudden, life-threatening emergencies. But how common are severe allergies? Allergies overall affect more than 30 to 40% of the global population, but severe systemic reactions are far less common. Food allergies occur in roughly 6 to 8% of children and 3 to 4% of adults, though prevalence is rising, especially in industrialized countries. Peanut allergy alone affects around 1 to 2% of people in Western populations and is one of the leading causes of fatal anaphylaxis. Insect venom allergy affects about 1 to 3% of adults, while drug-induced allergies, particularly to antibiotics or anesthetics, occur in up to 10% of patients but are often mild. True anaphylaxis has an estimated lifetime prevalence of 0.05 to 2%, meaning that roughly 1 in 100 people may experience it at one point. Despite their rarity, severe allergies account for a disproportionate share of emergency visits and death, highlighting the need for awareness, prompt recognition, and access to epinephrine. To conclude, allergic reactions remind us that the immune system's protective power must always be balanced by restraints. The same pathways that defend against parasites can become sources of chronic inflammation and disease when overactivated. In our next chapter, we will focus on one of the most impactful allergic diseases, asthma, to understand how chronic airway inflammation turns a simple allergic response into a long-term health challenge. Before closing, I have a small request. If you enjoyed this content and want to hear more, please like and subscribe. It's a small step for you, but it helps me a lot. So, thank you for listening and see you next time.